If we appreciate this, it is important for us to move from a physical vacuum to a vacuum which is Hartree-Fock itself. Okay. So, because all our correlation problems start with the vacuum, which is start with the Hartree-Fock. So, starting from Hartree-Fock, we are exciting. So, Hartree-Fock is our base reference. So, every time if I have to expand Hartree-Fock in terms of vacuum and A1 dagger, A2 dagger, etc., that becomes a complicated exercise. So, is it possible to think of a new description in which psi 0 itself is the vacuum, just like we are doing? So, we will not expand psi 0. So, what kind of description will make psi 0 as a vacuum? Okay? What is the property of a vacuum? Please do this practice problem later. Huh? These are practice problems you will be able to do. If you do not do, we will do it on Thursday. But I think this was only to show an important topic to which I am going. So, the topic is essentially that there is a simplification if I do not expand psi 0 in terms of the vacuum. So, otherwise every time I do correlation problem, my Hartree-Fock, psi Hartree-Fock has to be expanded in terms of A1 dagger, A2 dagger, etc., up to A1 dagger, AN dagger on the vacuum. Can I avoid this? I can avoid this if my psi Hartree-Fock itself becomes a vacuum. This exercise was an exercise in that direction, that do not expand psi 0, but make psi 0 as a vacuum, use these killer conditions. Vacuum must have a killer condition, right? That something annihilating, you can't annihilate. Clearly, I have not really been able to do this. I am saying A dagger acting on psi 0 is 0. A dagger is not an annihilation operator. So, how do I make sure that that is a vacuum? By suitably defining my operators. So, this brings to the concept of holes and particles. They are very, very important for correlation problem. So, instead of electrons, so far what we have done is the creation and the annihilation of an electron in an orbital. We are now going into a description where we create and annihilate what I call holes and particles. So, holes and particles are my new description, then you will see that this will automatically come. So, let me first define what is a hole. Note that I have a reference determinant Hartree-Fock. This is particularly true for the electron correlation problem, where Hartree-Fock is always my reference determinant. So, I define hole as absence of electron or a vacancy, absence or vacancy, okay, of an electron in one of the Hartree-Fock spin orbitals, which I call occupied spin orbital. If there is a vacancy, that means there is a hole. So, you have to think little differently. What is a particle? Particle is the presence of an electron, that is a normal thing. Presence of an electron in an unoccupied orbital or a virtual orbital. So, this is really normal annihilation operator and creation operator, but this is exactly opposite. So, if you look at now Hartree-Fock, psi 0, okay, in terms of holes and particles, note that when I said electrons, vacuum, physical vacuum is vacuum because it has no electrons. Now, try to think of Hartree-Fock. Does it have a hole? Hartree-Fock reference determinant itself. Does it have a hole? No, because there is no vacancy. Okay. Does it have a particle? No. So, then the Hartree-Fock, which is actually an electron, becomes a whole particle vacuum. It is not a physical vacuum. This is not a physical vacuum, but it is a vacuum in the sense that it does not contain holes, it does not contain particles. So, I should be able to define creation and annihilation operators not in terms of these, but in terms of holes and particles. Then I need not have to write such an unphysical statement that something annihilation equal to 0 and I have to keep track. Something creation is equal to 0 and I have to keep track of what it is. I can write everything in terms of annihilation operator, just as in the normal vacuum. Normal vacuum, you remember, any AI acting on the physical vacuum was 0. So, I want a similar structure that any annihilation acting on the Hartree Fock should be 0. So, how do I do that? Since it has no holes and no particle, let me first try to define creation operators for holes. So, how do I define creation operator for holes? Okay, this is no longer creation operator for normal electrons. So, how do I define creation operator for holes? From the Hartree Fock, I have to actually annihilate an electron in the Hartree Fock orbitals, right? So, let me define this creation operator as X, just to distinguish from the small a. A was electron creation operator, this is whole particle creation operator. So, I define a creation operator X A dagger as equal to A when A is an occupied orbital, because holes are always with reference to occupied orbital. So, this becomes my whole creation operator. So, whole creation operator essentially means, whole creation operator essentially means I annihilate an electron in the Hartree Fock. So, whenever A will act on Hartree Fock, it will actually generate a hole. So, I have actually created a hole. Is it clear? So, obviously, the adjoint I can define exactly the same way, that the annihilation of a hole is nothing but creation of an electron in the occupied orbital. Okay. So, if there is a Hartree Fock, of course, you cannot create, as I told you here, A dagger psi naught is equal to 0, which means you cannot annihilate, and that is the meaning of vacuum. Vacuum means you cannot annihilate, because why can't you annihilate? Because holes are not present. So, I can't do a whole annihilation operator. So, this is for the holes. So, I define creation and annihilation operator for the holes, and A must be occupied orbital, that is important. Because holes are only creation, annihilation in the occupied orbital, but exactly opposite. So, normal creation of an occupied spin orbital is actually annihilation of the holes and vice versa. Let me now define particles. So, for particles I am going to use virtual orbitals, because this is the presence of an electron in the virtual orbital. So, let me write this as xp dagger. I am again using A, B, C, D for occupied orbitals, P, Q, R, S for the virtual orbital. So, xp dagger, and this is nothing but AP dagger, standard definition, and xp is also equal to AP, where P is now virtual orbital. So, that becomes creation annihilation operators for the particle, which are standard. Xp dagger is equal to AP dagger, because I am just creating an electron. Okay. So, I am creating a particle. Is it clear, the definitions? So, now you can see, I will come back to this problem or any other things. So, let us see now that if I have a Hartree Fock, why this is a vacuum now, if there is reference to the hole and particle. So, let us assume that XA is acting on the psi Hartree Fock. Now, you see A is an occupied orbital. So, XA by my old definition is A dagger Hartree Fock, and we know that is 0, because I can't create an electron which is already present, or in other words, now there was no hole, so I can't annihilate. Now, I have to change the language. In terms of normal thing, I am saying there is an electron present, So, I can't create an electron. Again, in holes and particles, I am saying there is no hole, so I can't annihilate holes. So, what is important is, of course, look at this part, because I am now defining hole and particle. So, Xa acting on psi Hartree-Fock is 0, and similarly Xr or Xp acting on psi Hartree-Fock is of course 0, because Xp is nothing but Ap, particle is not present, so I can't annihilate anyway. So, now I am able to define two sets of orbitals, two sets of operators, holes and particle, whose annihilation on Hartree-Fock is 0, and hence I am arguing that the psi Hartree-Fock is a hole particle vacuum. It is not a vacuum in terms of normal electrons creation operator, but it is a vacuum in terms of hole creation, hole annihilation, or particle creation, particle annihilation. So, from this vacuum I can only create, either I can create a hole or I can annihilate. So, remember, when I was doing this problem, I had to physically remember that this is AA dagger. So, if I bring AA dagger here, AA dagger psi naught would be equal to 0. I have to physically remember, because A was occupied orbital. If I use this, then I do not have to bother. This will be like bringing regular annihilation operators to the right, whatever it is. Okay? And if I do that, then automatically I will ensure that the results are correct. Now, you can of course write the commutation, anti-commutation relationship between holes and particles, because they are essentially related to the creation annihilation operators of spin orbitals. So, you can easily write by taking the adjoint or wherever it is not necessary, like particles, it is exactly identical. So, you can actually see that they will follow exactly the same anti-commutation relationship, okay, between the two particles, between the two holes, or so on, or one particle, one hole. You can actually use the same anti-commutation relationship. So, that is very easy to do, and then we can rewrite the entire thing in a very simple way. So, for example, if I come back here, I can now rewrite this actually what I wanted to do, psi 0, because that is my vacuum now. Hartree-Fock is now vacuum. Now, I will not use physical vacuum, and then how will I write psi AR? How will I use psi AR? First one will create. Which one I will create first, A or R? All are creation now. I am going to write in terms of X. I am going to write in terms of X. Okay. So you are saying that I will do XR dagger, XA dagger, psi 0. Remember, now everything has to be creation. Everything has to be creation, because it is a vacuum now. From the vacuum you can only create, okay, unless of course this is equal to this, but this can never be equal to this, because one of them is hole, one of them is particle. So, between the holes and particles, the holes cannot be equal to particles, remember, because they are occupied set, particle is unoccupied set. So, there is a condition by which they can never be equal. Now, you can actually look at this as a vacuum, which means nothing exists. So, first I create A, then I create R. Okay, and then what I do is write psi AR as psi 0 XA XR, just take the normal vacuum, and then of course AI dagger AJ, XA dagger X, XR dagger XA dagger, psi 0, and start expanding this in terms of the anti-commutation relationship. Now, again you have to be careful here, because these are now ordinary creation annihilation operator, these are holes, particles. So, you can't use an anti-commutation between X and A. So, you have to actually write this in terms of creation annihilation by dividing this Ij between holes and particles. So, a subset of I can be hole, I can be particle, J can be hole, and J can be particle, and then write in terms of X. so that everything will become in terms of x, and then use anti-commutation relations. It looks very difficult, but actually these are quite simple things to do. Of course, there is a sum over ij, yeah, and there is hij. But the important simplification that comes in is the fact that this psi naught I do not have to expand, and this is very important for a large as n tends to infinity. In a many body problem where n becomes very, very large, this is a very important simplification, because otherwise there will be too many determinants, too many creation annihilation operators on both sides, either sides. Okay. Yeah, this particular problem, not, it depends on what is the problem. If I give you psi ar, theta 1 psi ar, of course there it will be. Okay. So you can actually do this problem. Yeah, this problem is fairly simple, as you can see. So you can divide I and j in terms of holes and particles, and then say that this is, then apply the anti-commutation between holes, between particles. Yes. Yeah. So you can call this, when it is hole, you can call this hole annihilation operator, right? This will then become hole creation operator when j is hole. When this is particle, they will have a normal this thing. So you divide into 4 subsets. I can be hole, j can be hole, I can be particle, j can be particle. So all 4 possibilities, right? So then it becomes easy to, yeah, just easy to break down, and many of them will just become 0. Actually, by very simple this thing you can actually make out what they are. See, note that aj is acting on psi naught. So what can be j? See if aj acts on psi naught, it cannot become 0. If it becomes 0, then the problem does not exist, right? So first of all sum over ij, aj has to be occupied orbital. J has to be occupied orbital, which means I am creating a hole. This should not be a hole annihilation. This should not be an annihilation operator in a whole particle vacuum. So J must be occupied, and I must be virtual. Okay, and then you can do the creation. And of that, you will see there is a delta AR condition. Basically, this will be A, this will be R. So that is all that will survive. Hij. So this will become R, and this will become A, this will become R. Hij, right? So this is I, this is J. So J should be A, I should be R. That is all that will come, because this is what is going to survive finally, right? So I know my first quantization result is RHA. So and you can actually see this, that this J must be whole, okay, because then only it can act on size. So this will be actually XJ dagger. This will eventually become XJ dagger, okay, or XC dagger or whatever. You have to sum, don't use A, you can use XB dagger also, sum over B, and this will become R. So sum will become B and R, and obviously then you will see by the second quantization that only B has to be equal to A and S has to be equal to R. So it's very easy to do this. So do this exercise, I mean it's very simple, because most of the terms will become 0. So only one term will survive. When this is occupied, this is virtual. This is the only term that will survive in all the 4 subsets, and you should be able to get HRA as a result. Okay, so the point is that for 2 electron, I gave you a first problem where it is a 2 electron, you expand in terms of physical vacuum, it was quite easy, okay, for 2 electron, but for large electron system this is not tenable. So that is why the Hartree-Fock vacuum becomes much simpler, so that you can expand everything in terms of hole creation, hole annihilation operator. So your theta 1 and theta 2, I can actually write in terms of hole creation and annihilation operator. So let's do that, and that is what I have actually used it. So let's say I write theta 1. Note that I have a AI dagger AJ. So I should write this as the following manner, theta 1 as both hole AB, okay. So then this will become XA dagger, XA XB dagger, okay, into HAB. So basically, I and J both are whole. They were AI dagger AJ, but because they are whole, in terms of X operators, they have changed. It has become XA XB dagger, correct? Plus AR. So now I is A. So AI dagger AJ. So this will become XA. AJ will also become now XR, HAR plus sum over RA. So now AI dagger will become XR dagger. This will become XA dagger. H RA plus RS, all particles. All particles, what will happen? Again AI dagger AJ. So this will remain exactly as it is, XR dagger XS HRS. So the same operator I can define in terms of whole creation, particle creation by taking Ij both whole, IA J particle, I particle J whole, both of them particle. 4 subsets, and I should be able to write. So this is exactly what I am doing. Instead of applying the AI dagger AJ, I am actually applying this operator. And then I am showing that only one of them survives in this case. The rest will all become automatically 0. I hope that is clear, huh? Because what I have done is I have written theta 1 as AI dagger AJ HIJ. Okay. So this was all I, all J. I have broken it up. So when I is whole, AI dagger is nothing but XA. So AI dagger is a creation operator in the occupied space, which is basically whole destruction operator, whole annihilation operator. AJ exactly opposite becomes XB dagger, and both of them are wholes. So one of them whole, one of them particle, only this changes. So this becomes XA, this remains as XR, okay. One of them R and A, then both of them become creation operator, and then one creation and one annihilation for the R and S. R and S, they will follow this, okay, because they are particle. So you can see that all combinations are given: creation, annihilation, creation, creation, annihilation. But this is in the whole space, this is in the particle space. Both annihilation, both creation. One of them whole, one of them particle, depending on which is whole, which is particle. If because whenever there is a whole and particle, I should be able to create both. There should be a possibility of creating both. But this now constitutes the entire form of the operator. When I act on a psi 0, depending on psi 0, depending on what I am acting on, one of these, some of them will become 0. Okay, their action will become 0. But this is the general form of theta 1. I can write similarly theta 2 is more complicated, but one can actually write a similar expression and then do the matrix element algebra. The matrix element algebra tells you that we get eventually in the first quantization what we got by Slater-Condon rule. So that was important because Slater rules gives us the matrix element. So exactly the same thing that we are getting. All right, I don't know if I will have time to do the 2 electron part. Yeah. Huh? Yeah, when it acts on psi 0, but this is the general form of operator. Yeah, actually it will be good if you can do this problem of psi 0, theta 2, psi 0 just once. If you can do it, it is again there in the exercise, either by using whole creation, particle creation, or by using normal creation annihilation operator, but just taking a physical intuition that only A dagger will act on psi 0. Is either way the same, whichever you feel comfortable. So please try to do once, at least in the exercise it is given, so that you are comfortable that you get this. So psi 0, theta 2, psi 0, just show that it is equal to half of AB minus ABB by using the expression of theta 2, which does not have a, remember, which does not have a antisymmetric integral, which is a regular integral. but there will be two conditions will come which will bring in the antisymmetric integral. Okay, so just expand this. A and B are of course occupied orbitals in psi 0. Theta 2 has a general expression, but I think by simple argument, in fact this is there for those who are interested should see this in the page 96 of Zaboslin textbook. So please see this. I am giving you as a kind of an exercise, so that you see. If you have a problem on Thursday, we can come back and discuss this. So this is a one problem at least you should be able to do, so that for the 2 electron also you are comfortable that the Slater rules are obeyed by these second quantized operators. All right. So let us we will go back now to the MP2 and try to write this in second quantized notation. Maybe in the next class we will see, and the diagrams. I told you the diagrams eventually simplify, not that the diagrams are necessary, but they simplify the notation, and later on it is very easy to go. E correlation at the MP2 level. Somebody can tell me the expression? 1 by 4. ABRS. ABRS, RSAB, I hope you remember why these two terms came. This actually came because of the Hamiltonian matrix element between 2 electron doubly excited determinant with Hartree Fock and conjugate of that, right. So this was the actual that matrix element, this is the conjugate. And 1 by 4 came because originally number of doubly excited configurations are actually A less than B, R less than S. Okay. Anyway, A cannot be equal to B, neither can R can be equal to S because of the Pauli principle, and we are talking in terms of spin orbitals. Okay. So if you look at the determinant psi ABRS, now can I write this determinant in terms of holes? Tell me. All 4. So XR dagger, XS dagger. Now you have to be careful, XB dagger, the way I have written, XA dagger. Note that I am creating a hole. Now I will talk in terms of holes. I am creating a hole. So this of course acts on psi 0, which is my vacuum. I am creating a hole A, which is actually annihilating an electron in the spin orbital, again remember. Then I am creating another hole B, of course A and B have to be different, and then on the B I am creating a particle X and a particle R on the A. So my original notation was, remember, AR dagger, AS dagger, AB A, sorry, AB A. That was my original notation acting on psi Hartree Fock. Now with the new Hartree Fock vacuum, I am going to use everything which is holes and particles, and everything is creation operator, just like you do in a normal physical vacuum. From physical vacuum you just start creating. So this determinant is normally called 2-hole 2-particle determinant. I hope the meaning is now clear. So compared to my Hartree Fock, which is a vacuum, this determinant contains 2 holes and 2 particles. My Hartree Fock did not have any holes and particles. That was a vacuum in terms of hole and particle. So all the nomenclature in the correlation problem will actually include holes and particles. So if I have a psi AR, this is called 1 hole 1 particle state, 1 hole 1 particle determinant. So it has 1 hole A, 1 particle R. This is called 2 hole 2 particle determinant. All right. So this MP2 formula, if you remember, had come from A less than B, R less than S, psi ABRS, so which is now 2 hole 2 particle state, V psi 0, which is a vacuum, psi 0 V psi ABRS, or reverse, it does not matter. Normally we would like it this first and this later, because we want to show this from psi 0 to psi 0, but does not matter, divided by the energy difference epsilon A plus epsilon B minus epsilon R minus epsilon S. So this contains matrix element as a perturbation operator with the vacuum and 2-hole 2-particle state. So this is now a 2-hole 2-particle state in my language. So it is a matrix element of the perturbation operator with respect to psi 0. Then remember, what did I do? I wrote the perturbation operator as 1 by Rij, sum over 1 by Rij minus V Hartree-Fock I. Remember, V Hartree-Fock I is very important, because that must be subtracted in the perturbation operator, because my H0 is sum of the Fock operator, right? So my H0 was sum over H of I, sum over H of I plus sum over V Hartree-Fock I, correct? So when I write V, it was sum over 1 by Rij minus sum over V Hartree-Fock I, because this must cancel. Eventually my Hamiltonian is this plus this, correct? However, the 1-particle operator did not bother us, because this is between two determinants, so it was 0. So you had actually only 1 by Rij, which transformed into this, and similarly this transformed into this, or rather this transformed into this transformed into this, does not matter, okay? So, and I got that expression. If we apply second quantization, now we know how to apply second quantization on this, I should be able to get the same expression. You know, this is something that is a part of the exercise that you can keep doing. So I have a 2-hole 2-particle state, I have a vacuum, and I have 1 by Rij, and V Hartree-Fock I. V Hartree-Fock I will anyway give you 0, that you can check. In fact, this may be a good thing to check in second quantization also, that if you do psi ABRS theta 1 psi 0, it is equal to 0. Expand theta 1 in terms of holes and particles, okay, and just show that this is equal to 0 by second quantization, okay. So don't assume by the first quantization is 0, but second quantization you can show this. So many of these practice problems you can do. So the point that I am trying to show is that they can all be derived from the second quantization. MP2, whatever expression that we are showing can now be derived from the second quantization, and the algebra of second quantization can be translated much easily in terms of diagrams. There are diagrams by Feynman, Goldstone, Hugenholz, there are several diagrams are there. We are going to follow mostly the Hugenholz diagram, which are easy to follow for the second order perturbation. So what I will do next time is to give you the relevance of diagrams in terms of second quantization first, and then show with an MP2 algebra how can I transfer this into a diagram, very simple diagram. Once I know the rules, then every time I can draw a diagram, I can write the algebra immediately. Diagram will be much simpler, and then I will show in the perturbation each order how can I construct all the diagrams.